Hello. Problem K, the towers of noiHa, is about distorted towers of Hanoi. In this problem, we have the classic setup with 3 pegs and n disks, but after we have played a sequence of valid moves in the shortest possible solution, a child has taken all of the disks from peg number 1 and moved them to peg number 3. And now we have a potentially invalid configuration, but we still want to make only valid moves, and we want to solve the towers in the fewest moves possible. And the task is to count the number of moves. So let's start with the very basics. In the towers of Hanoi, if we have the 3 pegs and we want to move an entire tower of n disks from peg 1 to peg 3, eventually we will have to move the largest disk. And when this can only happen if all of the other disks are out of the way, so we need to move the tower of size n-1 to peg number 2, and then we have the large disk free. This gives us the recurrence, that the number of moves needed for n disks is twice the number of moves for n-1 disk, because we need to move the tower here, then the largest disk, and then the entire tower to peg 3, and this solves to the well-known 2 to the n-1 total moves. And the fact that this is almost a power of 2 will be important in a moment. So we are given the input in base 2, and this is important in this problem, that the input can be very large. There can be hundreds of thousands of disks or something like that, and we are given the number of moves performed before the child came in binary. So we need to take this number and translate it into a configuration of disks as the first step. And luckily the digits in binary are exactly telling us what to do. So if the number is 21, which in binary is the 16-bit plus the 4-bit plus the 1-bit, then we see that the first 16 moves are the 15 moves to move the tower of size 4, and then the next move is moving the disk of size 5. So disk of size 5 goes to the appropriate peg, and then all of the bigger disks remained untouched. We are only dealing with the smaller ones. The next 4 moves, the 3 moves will move a tower of size 2, and then the next move moves a disk of size 3, and then we move a disk of size 1, and we have the configuration constructed. We can also do essentially the same thing backwards. If we have any valid configuration, then we can count the number of moves to go from there to the solution, which is essentially modulo the position of the largest disk, the number of steps to go from there to the beginning, because it's also a pyramid on one of the pegs. So we'll just do the same thing backwards. So in this configuration, for example, the 6 is already on the correct peg, so we don't have to do anything with it. The 5 is not on the correct peg, so what we need to do is, first of all, we need to move everything aside. So the disks 1, 2, 3, 4 need to go onto the middle peg, and then we will move the 5 on top of the 6, and then we will spend 2 to the 4 minus 1 moves moving everything else onto the top. So for this 5, we need 2 to the 4 moves from the moment we are moving it to the end of the solution. And in addition to that, we now have the remaining disks 1, 2, 3, 4, and we know that we need to get all of them into the middle peg. So now when we go to 4, we see that 4 is not on the correct peg, and we continue like this. So we are doing essentially the same thing as in the previous slide, but backwards. So now that we can count the number of steps to go from a configuration to a solved state, we are almost done, right? So let's look at the full problem. After the child made the big potentially invalid move, it has created something like in this picture. There are 2 possible cases to consider at the beginning. First of all, it is possible that the new configuration is actually valid. For instance, if the child makes the move immediately in the beginning, then they move all of the disks from peg 1 to peg 3, and we just have a solved tower. So if we have any valid configuration, we already know how to solve it. If we don't, let's look at this as follows. So in red, there is the biggest bad disks that is causing us problems. Below is the original content of the 3rd peg. In green are the disks bigger than the red one. And now, eventually, we will, during the solution process, we will at some point need to correct the only mistake that is in the current configuration. So the 8 that is on top of 3 in this example, at some point we will have to move the 8. And now many smart people would consider like just two possibilities, right? Either we move the 8 to the second peg or we move it to the first peg. And if we make this choice, then it is clear what we have to do. We need to take all of the white disks in this picture. Those are the ones that are potentially in our way. We need to move them onto the peg that we are not using. So if we choose to move the 8 onto the first peg, then 6, 4, 2, 1 need to go onto the second peg or vice versa. And this is the fastest way in which we can move the 8. And then we have a valid configuration and we can count the number of steps remaining. So we consider these two options and we pick the better of one of them. Is that all? No, it's not. Because consider a situation like this one. There is one more possibility. Before we decide to actually move the 3, it may be beneficial to move one of the bigger disks. Because look at the example provided here. This is actually the smallest counterexample to the previous solution. In this situation, we know that eventually we will be moving everything on top of 7. In particular, we want to move the 6 on top of 7. And in order to do that, we will need to move the 5 away from the 6. And it is clearly better to do it right now, before we put any more clutter there, than it would be to do it later when it would require to move all of the smaller disks before that. So here the optimal solution starts with just moving 5 from peg 2 to peg 1 and only then dealing with the 3. And what are the actual cases in general? So if we are doing some actions with disks bigger than the bad disk before actually moving the bad disk from its invalid location, there can only be exactly one such move, and this can be moving the topmost bigger disk from peg 2 to peg 1, because if we are moving disks that are bigger than the red one, we cannot put any of them on peg 3, because this would not be a valid move. And as soon as we move one of them from peg 2 to peg 1, then the only valid move left is to move it back. So there are only two more cases to consider, and actually only one of them matters. So if we had something here and something here, we would move all of those smaller disks on peg 3. Then we would move the topmost bigger disk from peg 2 to peg 1. And then we would do the same thing as on the previous slide. So now we would argue that at some point the optimal solution has to move this particular disk, the red disk, and it is optimal to always use as few steps as possible to clean up, then move it, and then finish as quickly as possible. So that's the full solution.